Okay, thank you everyone. Good morning, good afternoon, good evening for everyone worldwide, and thank you for joining us today. My name is Samah Abdullah. I'm a senior scientist at King Abdullah University of Science and Technology, KAUST, in Saudi Arabia. And on behalf of the organizing team, I am very pleased to welcome you for our fourth talk, actually, in this presentation series, HPSC, High Performance Statistical Computing. So just to have some logistics notes about what we have today, the talk will take about an overall 60 minutes, 45 minutes for the presenter and 15 minutes for questions and discussion. If you have any question in advance, maybe you can use the chat to put your question there, and we will collect all the questions after the presentation and go on them one by one. Also, for all of you, you should know that our talks are recorded and we are posting all the videos on our website, hpsc4science.org. I also want to mention that related to HPSC, we have an invited session at GSM 2026 under the title High Performance Statistical Computing, Challenges, Opportunities, and Future Direction. And this will be on Thursday, August 6, 2026 from 8:30 to 10:20 a.m. in Boston. Hopefully, if you will go to GSM, you can join us. So today I am very happy to introduce our speaker, Prof. Dorit Hammerling. She obtained her MA and PhD on 2012 from the University of Michigan in Statistics and Engineering. Then she got her postdoc at the Statistical Applied Mathematical Science Institute in the same program. And she then joined NCAR, National Center for Atmospheric Research, where she led the statistics group within the Institute for Mathematics Applied to Geoscience and worked in Machine Learning Division before becoming an associate professor in applied mathematics and statistics at Colorado School of Mines in January 2019. She leads a large research group working on data science application, computer science, engineering, environment, and she brings 2 decade experience working in consulting industry and national research lab. She received the early award from the American Statistical Association section on statistics and the environment in 2018, and the outstanding associate professor award of the college at the Colorado School of Mines in 2024. So I'm pleased to have Dorit today with us, and now the floor for you, Dorit. Go ahead.
Thank you so much. And thanks for this really nice introduction. I want to take 1 minute to also thank the team, Summer and Mary and Mark Genton here and Ying, who have done an amazing work bringing HPC to the statistics community for the last 10 years. They have great software. If you haven't checked it out yet, we have all benefited from it. And I want to also thank the HPC community, who has been really welcoming to the statistics community. And I've had the privilege to work on HPC systems and all my students for the last 10 years, and it has really been a game changer. So big shout out to that. So we are using WebEx here, which is new to me. So we are doing our best to share that. We couldn't go to full screen. We tested all this stuff right now. So I'll try to do the best to share my videos. I'm going to ask a question. Can everyone see my PDF video?
Yes.
Great.
Yes.
All right. So we won't go to full screen, but share it this way here. So I'm going to talk about a project that we have been working on at the National Center for Atmospheric Research for the last 10 years or so. As Samit said, I'm a faculty at the Department of Applied Mathematics and Statistics, but I still have a visiting appointment at the National Center for Atmospheric Research and work very closely with them. The work I'm going to present is there have been many people over the last 10 years who have been collaborators, but most closely I want to honor Alexander Binard, who is just finishing his PhD and has done a lot of work on this project, and Alison Baker, who is a computer scientist at the Center for National Research and has really led these projects, and many other people here. So when we think about HPC, yeah, we often think about really fast computing and all these kind of things, which are of course really exciting. But one side effect of that is that we end up creating really, really large data, and that can actually lead to problems because it's hard to store all this data. So that's really the theme of this talk here, compressing large spatial temporal data, how to do that right without destroying what we really care about the science in here. Did that work? Are you still seeing my screen here moving forward? Yeah. Okay, great. So the first thing I want to introduce is the National Center for Atmospheric Research. It unfortunately has been in the news a little bit because the current administration is not so keen on it, but let's hope things continue to go well here. It's a national center. I'm sitting here right now in Colorado. This is a particular spectacular image, how it looks. But it has been around since the 1960s. It's a federally funded research and development center. There's a few hundred people, experts working here. And the mission is really to understand the behavior of the atmosphere and related Earth and geospace systems. And NCA operates their own HPC system that's specifically designed for Earth system modeling and the scientific community. It's open to anyone who wants to do HPC research there if they're on a federally funded scientific mission here. I'm going to introduce briefly something called the Community Earth System Model. Many of you who work in this area might know it as CESM, that stands for Community Earth System Model. What that is an Earth system model to model what's going on in weather and climate, to study past, present, and future climate states. You can think about it as a virtual laboratory. So when people think if CO2 goes up, what will happen in the future, that these kind of statements are made with this virtual laboratories community Earth system models. And the reason it's called community is because it's open to anyone. The code is completely open. People can contribute to the code, and it's just hosted at the National Center for Atmospheric Research. It's a very complex model, large code base. We have done all kinds of work to make sure it runs correctly, about 2 million lines of code, which is obviously pretty large here. But most relevant to this talk, it produces a lot of spatial temporal data. So when we talk about spatial temporal data, just so this is clear for the context of the rest of the talk, we talk about data. The output is both spatial and temporal. Let's say you run this model and you might run it for 100 years. Yeah? You can output that model. It could be output as high as hourly, and on the spatial grid covering the whole globe, maybe 1 degree. In more potent model runs could be a quarter degree in latitude, longitude. So, and hundreds of variables that describe the state. So things like everything that covers the wind, the ocean, the temperature, the pressure. So a lot of data output here. So natural question is, well, why do we care about compressing these data? So as I had just said, we have these amazing HPC systems that allow us, that become more and more computationally powerful, that allow us to increase resolution and both in space and time. And there's literally no end in sight to how much data that leads here. I've plotted here up to, I think this was done like yesterday, the latest amount what the NCA campaign storage looks like. That's the storage drive where people can save their data that they want to use for science. And the y-axis scale is in petabytes. I think 140 is kind of the limit when it will be fully full here. And you can see it has been creeping up to that over, I think we're showing here the last 8 years, very radically. So storage is very costly. So in the new NCA HPC system, at least in the budgeting, when I followed it, most of the budget is actually by now spent on storage. So not so much on, this is just so important. So it's just good to keep that in mind, that we are literally spending most of the budget on storage for these scientific HPC systems right now. And storage has become almost a limiting factor for client science. So people do these extremely interesting high resolution runs, but then they have to face factors such as people telling them, well, you ran it every hour, you ran it on this very high temporal resolution, but we really can only save a value for once a month. And that is clearly, of course, suboptimal here. So we are thinking about as compression as a tool to be able to make other choices. Let's say the choice here would be that you say, well, you
Que no me sale el sonido, ¿qué pasa?
Excuse
Que
me?
no me sale el sonido. Ah, perdón.
Okay, no problem. Yep. So we want to look at compression as a tool to store less data with minimal information loss. So we could still say you compress the data, and that way we save a lot of storage, and you can still store it for every hour, let's say. I'm going to give you a little basics of compression here. This is going to be the one slide, so just introducing a few of the key terms. So the key idea of compression is really to represent a set of numbers by a smaller set of numbers. And I'm going to add to that now, and we want to contain what is really relevant. Compression is a two-step process. So first is the compression. So we have the original data, let's call it X, and we compress the data, and then it's stored in that format C that is much smaller. And then we have the decompression or reconstruction step. If you want to do something with this data, then you decompress it and you get this back, this X tilde here. And there are two categories of compression, so-called lossless compression. That is, once you decompress or reconstruct the data, the X tilde looks exactly like the original data. And then we have the case of lossy compression, where that reconstructed data approximates the original data, but it's not exactly the same. So lossless compression, that's what we all do if you send someone a zip file or something like that. That is, of course, a no-brainer. Everyone would say, well, no problem. If we can get it back losslessly, we really want it. It's unfortunately not very efficient for scientific data. So lossless compression relies on the fact that there's structure in the data and that we can basically discard that structure because we know what it looks like, and when we decompress it, get it back. I'm going to show you a study here that was done by our dear colleague Peter Lindström at Lawrence Livermore National Lab. And what you're seeing here on the y-axis are the compression ratios for lossless compression of the uncompressed to the compressed size. And you can see these compression ratios are really minimal. There's something like 1.1 at the most here for the burst. That means we would say 10% of the data storage. That's really not worth it. And the reason that is because in numerical model output, we have all these very random bits at the end, and they don't allow for compression, unfortunately. So this is, we can't really leverage any regular structure in this numerical data. So these compressors that work very well on other data, they don't gain very much at all in the lossless setting. Which, what that means, implies we really need to go lossy. That means we need to use lossy compression. And lossy compression is a really well-studied problem for audio, video, and image data, but not for scientific data. That's where it all comes from. We had the privilege to work very closely with compression experts from these other fields, and they helped us understand a lot of these details, but it was very interesting to think about what are the kinds of analysis and how is scientific data really different from what we care about image data. It's pretty fascinating. I'm sure all of you have watched films on your cell phones or things like that. The decompression ratios that can be achieved in image data are really outstandingly good, like something to 1 to 100, because there are experts out there who see what our eyes can actually perceive, and it's relatively little, actually. You can compress a lot out of video data. But it's a very different thing if you have people who study data in a lot of detail. So this data that comes out of these HPC models at NCAR, this is scientific data where we have climate models run for hundreds of years, and then people want to do all kinds of studies, such as studying extreme values in small locations, very subtle shifts in seasonal cycle. So the scrutiny and so on, energy budgets, derived variables, the scrutiny we want for these kind of data is completely different than somebody watching a movie. All right. So I'm going to walk you a little bit of what has been done at ENCA in the last 10 years working on compression. So in the early days, people really thought about compression in the context of an ensemble. And if you're not so familiar with climate science, I'm going to tell you a little bit about this. So the way people think about quantifying uncertainty or randomness in climate models and Earth system models is typically that they run these so-called ensembles. That means they start the model off with tiny, tiny differences on the order of 10 to the minus 14 in, let's say, a temperature, one single cell in the temperature. And because of the chaotic nature of these models, we then get an ensemble that has a certain spread. And people think about that as ensemble variability. So this is just random noise. So in general, when we want to make scientific conclusions, we want to make sure whatever we see exceeds the random noise that we see from the ensemble. So a natural way was to think about compression in that context, that people said, well, we want to look at these pixel-wise differences, that we look at how did the original and the reconstructed data compare in that context of an ensemble. And I'm just going to show you one little plot here where you see that histogram, that gray, this one variable, and this was done for these hundreds of variables, but obviously this is just an example to illustrate that, that you could see the histogram represents the variability in the ensemble. And all these colorful markers are what that specific data set, one of these ensemble members that was compressed, what that looked like compared to the ensemble variability. And you can see some of these compressed data sets, like this downward pointing red triangle here, that look really different. So you definitely wouldn't want to use compressors that made your data look so different that it looked completely different than the original ensemble spread looked. That's just an example of what the early work looked like. You can imagine this was extremely onerous because you had to compress everyone, check it, how it looks against the ensemble. This was initial work, but not something you could do on a large scale if you want to operationalize how you would do compression here. The next thing that happened was the so-called Pepsi challenge. So this is a very old photo here before point in time any one of us was really thinking about data compression. In the 1970s, you might have heard this thing that people had to close their eyes and drink a cup of Pepsi and a cup of Coke and say, well, do they actually taste this different? That was the same idea. We asked scientists to look at compressed and uncompressed data and say, can you actually find a difference? And there was a big group of scientists who volunteered to do that and spent some time really digging deep into saying, like, what do they actually look different? And it turns out that they could really find differences when they did smart analysis. But what wasn't really clear is they could figure it out, but did that difference actually matter? Did that difference actually change any relevant features of the data? So in the next stage of that work, what happened is that we asked scientists who were experts in certain types of analysis, let's say specifically, how do the extreme change, or what happens to causal relationships between variables, and what happens to derived variables, and so on. And ask them to really take a dig deep, not blinded anymore, say, take this compressed data apart, you see any differences? And I'm just going to show you some highlights here. All this work, by the way, is published work. I'll show you a reference list, I think, of 10 papers or so to all this. So if any of this interests you in detail, you can read it all up, and we can, of course, chat about it after this talk here. And I'm just going to give you an example here of one interesting study that Philippe Navot from a French research lab did. So what he did is he did this very interesting extreme value analysis where he looked at, this was also a 100-year-long climate run, where he looked at what do the extreme value, and specifically that the last parameter index in the third 3-parameter extreme value distribution, what is that range of that parameter in the ensemble data that wasn't compressed, and how does that range compare to what we see in the difference from the compressed and uncompressed data? So he did this very careful study for a lot of climate variables that people could care about, like maximum temperature or precipitation, and look extremes there. And it turned out that the range in the climate model ensemble, which is what we really think about as just natural uncertainty, was much larger than anything between the compressed and uncompressed data. So basically, one could conclude that compression really did not affect any of the extreme values. And we had another expert in causal analysis, where they did all kinds of causal analysis, again, on that same 100-year data to see what do the relationships between these variables look like, and do they change at all between the original and the compressed data. And even though this chart or this graph looks very different, it turns out that the only thing that changed in all this was this, I'm going to flip back here, there's this very thin purple looking zero line here. That was the only thing that changed here. So there's also a paper on that out, and it turns out for the really large part, the causal relationships were not affected in any meaningful way. Having said all that, many of these tests turned out really well, but it really wasn't all rosy, in the sense of there were some things that really turned out to be quite detrimental. One of them was derived variables. So this is a very simple derived variable, but people looked at the differences of certain variables, precipitation and evaporation, for example. Here's this example. These compressed data really stuck out. So there were many more complicated derived variables, but it turned out that small biases in compressors can really cause problems if they're systematic. And then we look at derived quantities that might be at very different orders of magnitude here. So another example here that really was kind of detrimental and wasn't something that was easily caught is if you look at these so-called velocity divergent fields, which are second derivative computations. So in the right corner, you see what the uncompressed data looks like. And you can see here in the bottom right is the uncompressed data, and in the bottom left here is one of the compressors that for otherwise looked really good. You can see this our uncompressed field here looks maybe like cooked spinach or something. Like you obviously, you can see if somebody studies velocity divergence fields with something people study really a lot in the context of extreme storms or things like that, this would of course be detrimental. So all that led us to understand you really need to be very careful and look at many different things to make sure compression isn't messing up certain properties of the data that could really affect studies that people do with the data, where we run all these models and create the data in the first place. And we did, following up on that, we did another study where we studied very closely, working together with two of the leading compression algorithms that are developed at two national labs in the United States, at Argonne National Lab and Lawrence Livermore National Lab. And we understood that you really need to understand the inner workings of these algorithms very well to have a sense for what are the artifacts or the potential artifacts that we need to look out for. We obviously won't go into any details here, but these are still the two leading compression algorithms for numerical model data. These SC algorithms on a very high level works by predicting following values based on what the values before were in the gridded structure, and you can then don't need to save these values if you can predict them well enough. Whereas the CFP works very different. They use a block structure and then leverage the fact that within this block structure, values can be very similar, and then you don't need to store them all. I'm just telling you that to show that helped us to really pick up any of these potential artifacts here. So what you can see here is we are looking here now at errors. That means the difference between the original and the compressed data in a temperature field using that CFP compressor. And obviously, you don't need to do any particularly sophisticated tests here to see that there's clearly structure in there. The fact that there's structure in there doesn't necessarily mean this is a bad thing, but you really want to be aware of it, again, because if somebody, let's say, studies very small differences in how gradients might change, you want to make sure they're not just picking up artifacts that result from the compressor. And I'm going to show you one more example here. Again, this is all published work. There's many, many more examples in this, where we looked very carefully at seasonal cycles, particularly in the very cold, extreme Arctic and Antarctic region. You see these red dots here indicate where these data points were taken here. And you can see on the left is what the original temperature time series looks like. Well, that's the black line. And overlaid are 4 lines that show the SC compressor at different, the CFP compressors at different levels here on the top row, and the SC compressors at different levels on the bottom row. And you can see if you look at the original data, this looks exactly the same. But then if you zoom in and standardize and look at just the errors, you see these artifacts here in the top row. We can see that the sign of the bias, so ideally what we would see, we would like to these all to hover just around 0. That's what we would ideally like to see, these error plots. But you can see there's definitely some structure being introduced here. And in the case of CFP, depending on what compression level you used, so like here in the orange and purple case, that bias has a slight shift. Again, this might not be meaningful, but because people do exactly that kind of work, that they say we want to very carefully look at if there's any, let's say, seasonal biases that are exacerbated by climate change. These are the things we really have to watch out for. And if you look at SC here on the bottom plot, this is an example where there was really not much difference between the different compression levels, but we definitely have an enhancement of the seasonal cycle. That means in the middle of the year, we are actually getting warmer temperature indicated just as an artifact from the compression. Again, I'm pointing out here what these arrows are showing us. It's only the difference introduced by the compressor. So those are these kind of things to be really vigilant about. Yeah. All right. All that to say, as a result of this, again, many, literally, I think maybe hundreds of people helped work on this. I want to, again, acknowledge them and all that work that went into that. We created a Python package called the LDCPy, the large data comparison for Python. And what that package does is you can feed in different data sets. Let's say you have 100 years of one model and then 100 years of another model. That would be an example. In our case, of course, we used it. You have this 100-year run of the original data and the 100-year run of the compressed data, and you can then compare it. And it allows you to do all this kind of very detailed, specific analysis where you can say, I want to look at these potential temporal features here. We have all this. I'm showing you some examples here that you can calculate. Contrast variances, these are how gradients change in both east and west, and looking at certain probabilities that a point is negative versus positive, and these kind of things. These are things that can be really useful. Of course, you could code this all up yourself, but it can be very useful, for example, to look at the ratio of annual harmonic means for the first frequency, 50 frequency values surrounding the annual frequency, and you can all customize this. It's very useful if you want to do this kind of work where you want to do these careful comparisons here. For example, here, there's an example here shown how these east-west contrast variances really vary, and how you have the original data on top, and in the middle you see that SC compressor that makes that really a lot, makes them a lot weaker, and that was something you would not pick up if you just looked at the data without doing this more sophisticated types of analysis where you look up at the data over many time frames here. This was any obviously good package. We have been continually adding new features to it and still taking requests if people are interested. It has been pretty widely used now, even for very different things, like, for example, people comparing model data to satellite data and these kind of things. All right. Having said that, so the next thing I want to talk about, so all this work, I would say for maybe the first 5 years was really focused on kind of getting a handle on what is the problem at all and what can we do about it, and making sure we are not messing things up. And more recently, we have really been working on how can we potentially operationalize and automate all this, because just to remind you, we are talking routinely that climate model, and I think this is pretty typical for other climate or Earth system models. the output on the order of 180 different climate variables, all spatial-temporal. And there are many different characteristics this climate variable have, and you really don't want to do these very detailed studies for every single variable for every time somebody runs the model and wants to share the data with the community. So we've really been thinking about how can we potentially best leverage this suite of compression methods and make sure for each variable we pick the compression method and the setting of that compression method that is ideal in the sense of that we can say we want to compress as much as possible, but without destroying any of these things that we care about scientifically in the data. And to that extent, we have done another 2 papers here on coming up with a suite of metrics that work well, that allow us to translate what we see as potential for artifacts using these LDC-Pi and other ways of analysis into quantifiable metrics that we can operationally run and say we want to use thresholds that allow us that if all these criteria are met, can we then make sure we don't introduce any of these artifacts? Yeah, as you can imagine, this is also still ongoing work, and we're trying to refine this right now. I'll talk about a little bit about this at the end. But it's an original suite that has really worked out pretty well over the last maybe 2-3 years that we have kind of put it through the ringer, is using a correlation coefficient tests for all between the original and compressed fill, using a Kolmogorov-Smirnov test to look at if there's any distributional shifts, looking at spatial relative error, and then something called the data structural similarity index. Maybe you've heard about the data structural similarity index, the structural similarity index without the data in front of it. That is a tool, it's called SSIM, that people in visual work have used for a long time to compare images to make sure that people don't perceive any differences. We have turned this, we have written a paper about how to do this on purely numerical data without the need to render an image to make it more efficient, and come up with that to look at that to make sure the data looks very similar. There's a paper just on that if that interests you. That's kind of interesting by itself. Without going into any more details, so we have come up with this suite of metrics, and the idea is now that once you allow, you pass all these criteria, let's find the highest compression ratio that allows you to do this. So you can do this by brute force checking each compressor at all the settings to then find out what this best setting is. So I'm giving you an example here. So what you see in the columns here is what 3 different standard output variables from that climate model. And you can see here that I'm giving you an example for the CFP compressor where you see like P6 means this is very conservatively compressed. It's very aggressively compressed, and it gives you the compression ratio of 14.3 here for the CCN3 here. But it doesn't meet that's the criterion here, one of these criterions. So we put here that data structural similarity index as 0.9995, so it has to be at least that good. Higher is better, and you can see some of these very aggressively compressed things where we would get great compression ratios, they just don't meet that. So in this case, the first compression setting, it would be that CFP 18, that allows us, that's the optimal compression level in the sense of that allows us to get the most compression still meeting all these criteria. Obviously, this is just a sketch here. The nice thing about this is you can automate that and then come up with optimal compression settings for every single variable. The huge drawback of that is, of course, you have to do this by brute force checking and compress every variable using all these possible compression methods and settings, and then find out what is the one that actually is optimal. This is, of course, extremely inefficient if we're talking about literally hundreds of thousands of fields. So the vision that we had is to say we really want an automated compressor selection where we wouldn't need to go through this brute force compressor checking, brute force checking method, but rather there would be already features about the data that allow us to predict the optimal compression setting automatically, just based on what we can detect in the data itself. And obviously, ideally, we don't want to do that just for one, but for all possible variables. So when we started that study, the idea was, can we find generic features that predict the optimal compression setting for these hundreds of variables? So this is the last large study I'm going to talk about and give you some insights on that. So for that study, we used 183 climate variables, and these are really different from each other in some sense. Like some are mostly discrete variables, have a lot of structure, some are very smooth fields, and so on. We have thousands of time slices. That's really nice. So we can basically, we have an unlimited supply of having different time slices of the spatial fields of the same variable. We tried 7 different compressor settings, different compression methods, and different levels of each compressor here. And we don't wanted to do a study where we use explicit feature models. You'll see the one we actually set it on was something like a random forest, where we feed it explicit features, things like what are the gradients, smoothness features, contrast variances, many of the other things I've talked about before. And then also use implicit models, such as convolutional neural network, to see, can we actually discover any new relevant features? So that was our hope, to see, can we actually look at these, both try these modeling approaches in together and see if we can actually learn from each other and learn new things using this. So to explain this here, so this is a supervised learning approach here, in the sense of that we use the label data, meaning what the label is telling us what is the optimal compression method using that brute force technique here. And we ran this all on 1 degree data, that's very close to 1 degree data, that 192 by 2.88 lat longitudinal times 0 theta from the CSM large ensemble output here. And in order to label that data and come up with that ideal compression setting, the criteria we used here is what I've pointed out to you before, using that data structural similarity index, Pearson correlation, and the Kolmogorov-Smirnov p-values here. For the result I'm going to show you, what we actually published was using only that one compressor method at the different settings, because it was very difficult to learn across compressors. We kind of reduced the scope here. And then we'll go a little bit more into detail for these explicit feature models and which of these features are actually important, and the implicit feature here. And we tried a lot of different things. I think we tried every classification method that you can think about if you teach a classification class, to see what actually works best. Turned out that random forest turned out actually the best here. And when we started this project, I think we used on the order of over 30 different features to see what combination of these would actually work best. It turned out that none of these features by themselves, or even in better combinations, separates the classes very well by itself. So this was really a lot of work to kind of narrow down what actually works. And for the replication, these final 2 models that we actually ran with was a random forest model. I don't need to go into details, but you see the specification here, what the specific structure of that model looks like, and a convolutional neural network. Again, without, you can see here what the actual details was. We tried a lot of different things, and also tools to optimize what the actual model structure looks like. And we settled on 9 different features that turned out to be the most meaningful, without going into any details, but you can categorize them into these features that describe gradients. That means how things change in north, south, and east-west direction. Features that give you an idea about the smoothness, like how smooth are these fields, with the general idea that the smoother field is, usually the easier it is to compress. And a category of features that give us an idea about information contents. So these are specific things, entropy, and then something called the bitwise real information content that I'll briefly mention at the end. And we really had to reduce the scope as well. It turned out that we couldn't predict individual classes at all. Yeah, so we couldn't really say anything about should it be between 10 or see 10, the compressor setting 10 or 20, 12. But what we could do is categorize between the variables that could be aggressively compressed. That means using a much stronger compression ratio compared to the variables that are conservatively compressed here. And we categorized basically a group of these compressor settings as aggressive and a group of them as conservative. And you can kind of see that 16 is the line that separates these two between aggressive and conservative. And it turns out that both the CNN and the random forest model could do this kind of classification perfectly. So when we assess these models, and again, this is obviously described in a lot of detail in the paper, we always left out the specific variable and only trained the model on all the others. And in that setting, you can really predict perfectly whether you can generally compress aggressively, conservatively. That's already hugely useful because in practice, that means you don't have to try all these compressor settings. You can just try one of them on that in the conservative range, see how that works, and then just do one increment in each direction to make sure you actually found the ideal one. So this was very useful in practice. An interesting side aspect of that work was to see how useful these features were across variables and how consistent they were. And it turned out that they were actually quite consistent across variables. And the one that we have worked a lot since to see if we can narrow it down on this, but with this entropy and real information related features, because the nice thing about why we would ideally like to use these fewer features is because ideally we wouldn't like to run complicated models on that. Ideally, we would like to have one metric we can quickly calculate on the data and then it automatically determine what the compressor would look like. So here you just get an idea about what these look like. It turns out that the smoothness-related features, these north, south, east, west contrast variances, and the entropy and magnitude range and real information were really important. And we have been working in that direction since. One additional work of this study was once for an individual climate variable, also being less ambitious and say for an individual climate variable, there's some small distinctions. Let's say if we pick one of the ones that is a precipitation variable here, a snow-related precipitation variable that's called PRECSL here. You can see that variable lives in the optimal compression setting. It can be both 10, 12, and in a few cases 14. We were looking at, can we actually predict that's very fine graduation of these, what exact within this aggressive class of compression settings, can we predict what exactly for this given time slice, what the optimal setting would be. And here you can see the results again, that hardly worked at all. There were very few variables where we were successful. Otherwise, even though Alex and two other people basically spent a year trying to find this, we really couldn't find features in the data that helped us come up with these very fine distinctions here. So that part is still kind of ongoing research. And with that, I'm going to show you a list of references of all that work here over the last 10 years. I'm glad to share, of course, and you can any of these papers if you're at all interested in this type of topic here. And I'm going to just finish with one large starting slide and discuss some ongoing work here. That's really exciting. So I've been looking at the so-called real information content, and what that refers to is spatial correlation in bit planes. Well, so I'm giving you one example here where you have what that grid cell looks like. And we normally think about, when we think about compression, thinking about representing data the way we normally look at data here in a regular decimal kind of place here, where we say 2.83.15 compared to 279.64 here, for example. And then we think about, well, can we cut off any of these last digits here because we don't care about it? But the real information content represents data in binary and then looks at the spatial correlation in that binary setting and then tries to find out which of these bit planes is not relevant anymore and only noise. So we have been doing all kinds of exciting work here. Obviously, for the sake of time, I'm not discussing that, but it has been fascinating to look at that. I'm glad to talk to people about it. We're pretty close to sharing a paper on that as well here. With that, I'll end it and thank you so much. And I hope that was interesting, and I'll stop sharing here.
Thank you so much, Dorit. I learned a lot from your talk. So I do a different type of compression, which is in the operation side. So multi and
Cool.
mixed precision. So I think it would be good to combine both. And obviously the error will compound, but it saves storage and also time.
Yeah, mixed. They have actually done some work in mixed compression on verification settings. Fascinating too. And sometimes it works really well, and sometimes it doesn't. And you really have to understand the role in the code. Yeah, I love to talk to you about this. Yeah.
Yeah, so we have about 15 minutes for Q&A. If you have a question, please feel free to unmute yourself or type it in the chat. I will read the questions if there are any in the chat. Josh Jacobson, can you please unmute yourself?
Yeah. Hi, Dorit. This is Josh Jacobson at CU Boulder.
Hi, Josh.
Really nice talk. That's a really cool idea. And I have a couple of quick questions.
Sure.
So I would think that data with different, or like maybe data corresponding to processes with different types of properties, like non-stationarity or the
Yep.
ones that are non-Gaussian, say. So for example,
Yep.
maybe like a process like temperature as opposed to precipitation.
Yep.
Would maybe be differ in the technicality of the compression. So
Yep.
have you seen or have you had difficulties with like some of like with different types of processes being more challenging to compress?
Yeah, no, that's an excellent question, Josh. Yeah. So that is so one thing that you pointed out really thoughtfully here is, let's say, temperature and precipitation, because that kind of makes a lot of sense to people. So one key characteristic is that temperature is really a smooth field, versus precipitation. We have this fact that we have many areas where it's zero. Yeah, and you're absolutely right. Yeah. So some compressors, the ones that rely on smoothness, like this predicting from other values, don't really work very well in that setting. Yeah, but the ones that have these block structures, they actually work much better. For example, in these many areas where we actually have zeros, they work extremely well because they can, of course, save a lot of space because we know it's zero. One very fascinating artifact of that is that many of the climate models, that they have that weird feature that instead of putting out real zeros, where there should be zero for precipitation, that they send these very tiny values. So as part of this work, we have actually kind of detected things that are just kind of not make sense in terms of how the climate models are run. So people have actually worked on cleaning that up better. And you're absolutely right. Yeah. So the reason we don't just run with one compressor is exactly that the actual structure of these variables can be very different. Yeah, and there is not one optimal compression setting. I didn't make that so clear in the talk, but that's exactly absolutely right. Yeah. So
no, I think I saw on like slide 24 or 29
yep.
something that we've got all these different types of compression methods, and
Yep.
probably for some of these different fields,
Yep.
methods that have certain properties will be more suitable. So
that's very astute of you. You're absolutely right. What do you do, Josh? Are you a climate scientist?
Oh, a little. Right now, I identify as a statistician, I suppose.
Okay. Wow.
Yeah.
You really know a lot. Yeah, that's awesome. Yep. No, totally right. Totally right. And that's where okay, I'm gonna say one more thing because it's so interesting, because we just worked on that real information content thing that I was telling you about in the bit planes. And that is fascinating by itself, because the variables like the precipitation, they actually introduce structure now, because the bit planes, they actually pick up the fact that we have areas where it's strictly zero and we have areas where there's something going on. Yeah, so we actually artificially having much more supposedly real information in this very down like 30 digits down in this bit plane. So we have to also work around that way. Yeah, so it's fascinating. Yeah, just to say, yeah, you're absolutely right. The structure really matters. It's probably the key thing to actually determine what's going on. Yeah.
So a second quick question. In the like machine learning, deep learning area,
Yep.
one of the common tools right now is variational autoencoders and
Yep.
decoders.
Yep.
And I wonder, like, if you were to train maybe like one of those models for maybe multiple processes or even just individual processes,
Yep.
you could kind of store those parameters of those encoders and decoders. Yep. And then the only information that you need to store for the data is just like the latent space, the
Yep.
encoded space. Is that something that you've like worked on a little bit or thought about already?
Yeah, we have thought about it. So this is I would say what you're talking about falls a little bit in the broader realm of emulation. Yeah, where you say, I really want to store what's essential about the model. Yeah. And that's of course, that makes a ton of sense where you want to do this. It's a little removed from these compression settings where people are currently really looking at these minute differences. What you are saying is more like, if we have these models do this, maybe still fall within the general structure of what these ensembles look like. Yeah. Mm-hmm. I didn't talk about this, but I've been involved in some of these projects. So this is kind of different because we are really looking at more like, is the overall structure preserved? Yeah. So this is a little removed from this what I would say very detailed work we do in compression. But having said that, the key thing with using something like autoencoders is to preserve the correlation structures between these 180 variables. That's very difficult. So you can train on some subset of them, and I think they do really well. But what the general criticism is because you have these very highly nonlinear features, and is that actually preserved? And I think that's really the big open question now, with also these big efforts that have been going on with Microsoft, where they create the machine learning style models, and there's a lot actually happening here at NCAR in that realm.
Right. Yeah, awesome.
Mitch Groff has a really nice paper actually with your colleague Will Kleiber that I was also only like a little bit involved in, but they have really done the work. You might be familiar with that. Yeah.
Well, awesome. Thank you so much, Dorit.
Thank you.
Any other question? Mark Jenton has a question.
Hi, Dorit. Thanks again for a very nice talk. I have actually two questions related to the level of compression.
Yeah.
So the first is that the level of compression must depend on the type of question or analysis you want to do with a given variable. Let's say if you look at temperature, if you're interested in temperature trends or in extremes of temperature, then probably you don't want the same level of compression. I mean, unless you want a compression that works for any type of analysis, but then probably you cannot compress too much, is my guess. That's
I think you could not have said that better, Mark. Yeah. So that's a great question. Yeah. So if we have a custom goal in mind, you can compress much better, because exactly like you said, then you can just compress to preserve exactly what you care about. That unfortunately for these like the CMIP, this climate model intercomparison project, that's exactly, we really have to be most conservative, that we say any type of analysis that anyone could possibly do, we don't want to destroy it. This is a very conservative level for these general data sets that are shared with the world. But you're absolutely right. Yeah. If you know what you want, you can compress what you want to preserve, and you don't care about the rest, you can compress way, way better. Yeah.
Yeah, okay. And then the second part of the question is that, I mean, you can compress marginally for each variable, but eventually in a future analysis, you need several variables. So it seems to me that just compressing optimally marginally is not jointly optimal. I mean, it's like from a multivariate distribution, you can have all the marginal to be Gaussian, but we know the dependence, you can have many couplers and many type of dependence. So it's a bit the same problem. I feel that if jointly several variable you need down the line for your analysis, then you need also to take this into account, and you cannot just compress marginally, right?
Absolutely. That's why in these packages, we have built in these derived quantities, and obviously they are not all possible combinations, but we have a whole slew of derived quantities of things that often have 2, 3, 4 variables included that people really work with, such as energy budgets, these derived fields that might include many more variables. So we are indirectly accounting for that because we have built them in and we make sure that the metrics we have, but obviously this is a clear problem. It's just how can you practically do that in order to really make that work. But there's like I said, there's the known analysis types that people use multiple variables for, we have included.
Yeah, okay. All right. Thank you.
Any other question while Dorit is with us? Mark, are you still raising your hand? Your hand is still. Okay, no.
1, 2, 3. We can also just chat. We have what? 2 more minutes, 3 more minutes. I saw that Richard and Lilis are here that I would say hi to.